Hello everyone. I will start the review for exam 3 from the formula sheet, chapter 9, 10, 11, and 12, which are the content of exam 3. The important thing about the formula sheet, it has all the equations that you need to solve any problem in the exam. You just need to know how to use those formulas. Initially, I'm going to go over those formulas and what do they mean, because if you understand the equation, you'll be able to use it in the right place. And if you don't understand it, you'll use it in the wrong place. Chapter 9 is about conservation of momentum and the center mass equations. The first equation here is the equation of momentum. So P stands for momentum, and it's a vector quantity, and momentum is equal to mass times the velocity. Now, the thing about momentum, it's conserved when the net external force is zero. So if there is no external force acting on the system, meaning all the forces are internal to the system, not external, in that case, we say that the momentum is conserved, meaning the sum of the momentum before any event is equal to the sum of the momentum after that event. So if you have mass 1 and mass 2, and they have velocity 1i and 2i before the event could be anything, collision or explosion or sudden movement of a system, will be equal to the momentum after the event. Now, if there is an external force, the sum of the external forces or the net external force on the system will be equal to the rate of change in the momentum, delta P over delta T, where delta P is the change in the momentum over time. Now, one of the events where the momentum is conserved is collisions, because collisions are forces within the system. So two objects hit each other. This is internal forces. There is no external force on the system unless there is friction. In the case of collisions, the momentum is conserved. But collisions could be divided into elastic and inelastic collisions. In both cases, the momentum is conserved, but in the case of inelastic collision, the kinetic energy is not conserved. Kinetic energy is only conserved when there is elastic collision, where there is no energy loss during the collision due to friction. So only in the case of elastic collision, the kinetic energy is conserved, meaning the sum of the kinetic energy before the collision is equal to the sum of the kinetic energy after collision. So we get this equation, and from it we can derive this equation for the velocities before and after, assuming we have two objects colliding. The second part of chapter 9 is about center of mass, where each object has a center of mass. We can represent this object by a point mass, where this point mass is basically the center of mass of that object. And we can calculate the center of mass by adding the mass times the position of each particle in that object, divided by the sum of the mass of all those particles. And we can do it for the x-coordinate and the y-coordinate. And from there, we can find the coordinate of the center of mass. And we can apply the same thing for the velocity of the center of mass, where basically it will be the sum of the momentums of all the particles that make up that object divided by the sum of the particle masses that make up this object. So that's regarding chapter 9. Chapter 10, we start talking about the rotational motion. And we start by conversions here. There are three types of units pertinent to angle. One of them is the one we know, the degree, where the one revolution is 360 degrees. And there is radians, which has to do with the length arc of a circle, where pi is half the perimeter of a circle and 2 pi is the complete perimeter of a circle in terms of angle. And we have revolution, where one revolution means a whole cycle. Now those are related to each other based upon this equation. One revolution is 360 degrees and one revolution is also 2 pi radians. Now when we deal with arc length, we are dealing with radians. So for example, the length of this arc is related to the angle in radians. And this arc S is equal to the radius of the circle times the angle in radians, where this length here represents the radius of this circle, assuming this is a complete circle here. Now, the speed of any object, the tangential speed of any object in a circular motion, will be equal to the arc that this object traveled divided by the time taken to travel this arc length denoted by s. Now, any object in circular motion has centripetal acceleration that keep it in circular motion. And of course, this centripetal acceleration is related to the centripetal force, because we know objects in rest tend to stay in rest, while objects in motion tend to continue moving in a straight line. That's Newton's first law. Objects in motion tend to move with a constant velocity, means constant speed and constant direction. So it's abnormal for the object to rotate. If it's rotating, then there is a force causing it to rotate, and this force is called centripetal force, and it's related to the tangential velocity of that object. Now, centripetal force could be any type of force. It could be, for example, the force of gravity, like the moon revolving around the Earth. What keeps the moon from moving in a straight line is the attraction between the moon and the Earth, and this will represent the centripetal force that will cause the object to keep moving in a circular motion. The reason the moon is not plummeting into the Earth because it has a tangential velocity v, and this tangential velocity is enough to overcome the curvature of the Earth so that it's not plummeting into the Earth, while it's still falling, of course, toward the Earth, but it's falling in a controlled orbit. mv squared, where v is this tangential velocity, over the radius of the orbit, has to be equal to the centripetal force, whatever the centripetal force is. It could be, as we mentioned, gravity, like in the case of Earth-Moon system or Sun system, or it could be, for example, the tension on a string. If you are holding a string with, let's say, a bucket of water, the bucket of water is inverted. The reason the water is not falling because it's moving in an orbit around your hand here, caused by the tension on the string. So if this velocity is enough to create this equilibrium between the centripetal force and the force of tension, mv squared over r is equal to the tension in that case. So the tension has to be equal to the mass of the cup times the velocity square of that cup over the radius of the orbit of that cup around your hand. Okay, and this is also applied when you make a turn, when you're driving your car and you are making a turn. The reason you are able to make a turn is that the centripetal force, which is in that case the friction, the static friction between the tires and the road, is equal to mv squared over r, where v is the speed of the car. So if you increase the speed so that mv squared exceed the friction, in that case the car will skid and you'll not be able to make the turn. So centripetal force could be any force that keeps the object in a circular motion, and this force has to be equal to the mass of the object times its velocity, tangential velocity squared, over the radius of the orbit of that object, in order for the object to move in a circular motion or in an orbital motion as we describe it. Okay, so this equation is very important to understand its implication and when it is applicable. Of course, in the case of the road and making turns, there is also bank road, which give another layer of safety that enable you to make a turn, which is the angle between the road and the center of rotation. And in the book, you'll see the derivation of the maximum centripetal force on bank road, which incorporate both the friction part, and also the angle associated with the normal force. When we talk about rotational motion, we have the term frequency, the number of circles per second or number of revolutions per second. And frequency is the inverse of the period of the rotation. The period is the time taken to complete one revolution or one rotation. So frequency and period are the inverse of each other as long as the units are consistent. So if the frequency in revolution per second, the time or the period will be a second per revolution. Also, we can derive a formula for the tangential velocity in terms of frequency and period. Remember, tangential velocity is the linear velocity for an object moving in a circular motion. When an object is moving in a circular motion, there is omega, which is the angular velocity, and there is v, which is the tangential velocity at any moment. So at this point here, this object, which is moving in a circular motion, has tangential velocity in this direction. Then here it has tangential velocity in this direction, and so on. Of course, the tangential velocity is changing direction because there is centripetal force. Centripetal means center seeking, so there's centripetal force that is directed toward the center of this circular motion, F sub c, and hence there is centripetal acceleration as well, A sub c, that cause the object to continuously changing direction so that it stays in a circular motion. So the tangential velocity of an object moving in a circular motion will be equal to the distance over the time. And in that case, if the object completed one revolution, the distance will be what? The distance will be the parameter of that revolution, the parameter of the circle that represents one revolution. Okay, and we know the parameter or the circumference of a circle is 2 pi r, right? So this is the length that the object traveled to complete one revolution. And of course, the time taken to complete one revolution, we call it what? We call it the period. The period is the time taken to complete one revolution. So to find the tangential velocity or the average tangential velocity, you can divide the circumference by the time taken to complete one circle. And this time is the period. So it's 2 pi r over the period. And if we replace 1 over t by f, since the frequency is 1 over t, then the velocity will be 2 pi r times f. And we'll be using those equations more in chapter 13 and 14 as well. And since we know that the centripetal acceleration is v squared over r, the negative sign here means toward the center, then we can take v here and plug it into this equation here, v squared, so we have to square it, divide by r, and this will give us the centripetal acceleration, which is this equation here. And of course, centripetal force is the mass times the acceleration. Force is always mass acceleration, and hence the centripetal force will be this equation. Keep in mind that the angular velocity has to be in radians per second here when we talk about circular motion. Now to put everything here together, since the angular velocity is the change in the angle over the time taken, recall v is s over delta t, where s is the arc length, r times the angle. So basically v is r times delta theta, where theta is the angle, over delta t, which will give you this equation here. And since delta theta over delta t is omega, v is r times omega. And recall that when the time is equal to the period, omega can be replaced by 2 pi over the period. And therefore we can write the centripetal acceleration as omega squared times r. And the centripetal force is the centripetal acceleration times the mass m. We have the angular acceleration, which is the change in the angular velocity over the change in time. The same way, acceleration is the change in the linear velocity over the time. We replace v by omega here since we are talking about angular motion. And the same way, there is tangential velocity. There could be tangential acceleration if the object is accelerating. Okay? Alpha could be 0 if the angular velocity is constant, or it could be positive. Alpha could be positive if the angular velocity is increasing in the counterclockwise direction, because counterclockwise is positive, or alpha could be negative if the angular velocity is decreasing in the counterclockwise direction. Of course, if it will be the way around if omega is in the clockwise direction, because clockwise direction is considered negative. Keep in mind here in rotational motion, counterclockwise as positive. This is counterclockwise motion. This is considered positive. While clockwise rotation, this is clockwise rotation, is negative. Omega, we replace v by omega, which is the angular velocity. We replace a by alpha, which is the angular acceleration, and we replace the displacement x or y with the angle theta. Okay. Keep in mind, in the case of rotational motion, we have angular velocity and we have tangential velocity. And also we have angular acceleration, tangential acceleration, and centripetal acceleration. 3 types of acceleration are possible in the case of rotational motion. And now rotational motion has inertia. The same way in the case of linear motion, the inertia or the resistance of the motion is mass. The mass represents, in the case of rotational motion, we call it moment of inertia. So instead of mass, we have something called moment of inertia, and that's the resistance to rotation. So the bigger the moment of inertia, the harder to rotate the object. The same way in the case of linear motion, the bigger the mass of the object, the harder to move it, the harder to accelerate it. Remember, the acceleration is inversely proportional to the mass according to Newton's second law, because the bigger the mass, the smaller the acceleration. In the case of angular motion, the force of rotation will be inversely proportional to the moment of inertia. Of course, the force of rotation is called torque, which we addressed it in chapter 11. But you need to keep in mind that moment of inertia is equivalent to the mass in the case of linear motion. Moment of inertia does not depend on the mass only. It depends also on the dimensions of the object. So we can calculate the moment of inertia using this equation, where this equation tells you that the moment of inertia of any object that is composed of several particles is equal to the mass of each particle times the radius square of that particle, where r represents the distance from the individual particle to the center of rotation. And from there we can find the kinetic energy of rotational motion. We call that the kinetic energy. In the case of linear motion, it's 1/2 the mass times the velocity squared. This is in the case of translational motion or linear motion. Now here, instead of m, we are using I, as you see here, and instead of v, we are using the angular velocity, omega squared. Now, if an object is rolling without slipping, then you have both. You have rotational motion and you have translational motion. So the total kinetic energy of that object that is rolling without slipping is equal 1/2 times the mass times the velocity, where the velocity here is the translational motion of that object, where the velocity here is the translational velocity of that object, plus the rotational kinetic energy. So if you imagine here like a disk that is rolling, and of course if it's rolling, then it's moving. So after a while it will be here, travel certain angle. So if this point is here, now this point is here, and the object has moved certain distance, d, where distance is equal to the arc here, because it went from this point to this point. So this length here is equal to this length here. Okay, so the object here has a translational motion v, and it has also rotational motion omega. And the total kinetic energy of that object is the sum of the kinetic energy of the translational motion plus the kinetic energy of the rotational motion, 1/2 I omega squared. You push the object here, you apply work, and recall work is force times distance. We know that the work will be transferred to change in the kinetic energy. That's the work energy theorem that we studied in chapter 7 and 8, but at that time we did not include the rotational motion. So when we talk about applying a certain work on two objects that have the same mass, the change in the kinetic energy will be the same, because you're applying force times distance on two objects that have the same mass, so m is the same, hence the change in the kinetic energy will be 1/2 mv squared for both of them. If you give them the same force over the same distance, meaning the same work, they will end up with the same kinetic energy. But when we have a rotational motion involved, there is the moment of inertia is involved here. So if you give two objects the same work, even if they have the same mass, if their moment of inertia is different, they will have different total kinetic energy. Because the one that has more moment of inertia, it will take it more work to achieve the same kinetic energy as an object with less moment of inertia. So if you push, let's say, for example, here, if you look at the moment of inertia, let's say for a disk rotating around its axis versus a hoop rotating around its axis, you can see the moment of inertia of the disk is 1/2 the moment of inertia of a hoop. Even if they have the same mass, assume you have a hoop that has the same mass as the disk. Here, disk and the hoop have the same mass. If you give them the same amount of work and get them to rotate and hence move, which one will be faster, the disk or the hoop? The answer is the disk actually will be faster, because even though it has the same mass as the hoop, it has less resistance. And since it has less resistance to rotation, it will attain more velocity because it will rotate easier. And of course, rotation translates into translational motion. So although the mass here is the same, I is different. And when you have bigger I, you need to give it more work to achieve the same total kinetic energy. So keep that in mind when you deal with problems that involve total kinetic energy of objects that have the same mass but different moment of inertia. This table tells you the moment of inertia of different objects depending on their shape and also depending on the axis of rotation. They are rotating around what axis? So here, if the disk is rotating around its center, its moment of inertia is 1/2 mr². But if this same disk is rotating around its rim, in that case, the moment of inertia will be 3 times bigger, because it's harder to rotate it around its rim compared to rotating it around its axis. Rotating it around its axis is 3 times easier. Okay, the same thing here. You have a sphere rotating around its center versus a sphere rotating around its rim is around 3.5 easier than rotating it around its rim. Because this is 2/5, this is 7/5. That's 3.5 bigger moment of inertia. All right, so you need to keep in mind here regarding moment of inertia, it depends on not only the type of object, but also the distribution of the mass around the axis of rotation. Okay, on chapter 11, we talk about torque. Torque is the force of rotation, and it depends on the force applied and the lever arm. So if you have a rod here, and suppose this rod is rotating around this point here, where the axis of rotation is into the page, and if you apply force here, this force will cause the object to rotate. Now, what causes the rotation is the component of the force that is perpendicular on the lever arm. So this component here. And the lever arm is the distance from the axis of rotation to the point where the force is acting. So if this angle is theta, the force that is causing the rotation will be equal to F times sine theta, where F is this force. This equation tells you, this equation is similar to Newton's second law. If you recall, Newton's second law is the sum of the forces on the object is equal mass times acceleration. Here we are talking about rotational motion, so the force will be the force of rotation. So F is replaced by the torque, tau, this symbol, tau, and the mass is replaced by the moment of inertia, I, and the acceleration is replaced by the angular acceleration, alpha. Now there is a term called static equilibrium. Static equilibrium is different from translational equilibrium or rotational equilibrium. Just to explain here, if you recall, if the acceleration is 0, this means that the sum of the forces is equal to 0. And when the sum of the forces is equal to 0, you have two possibilities, right? It's either the object is at rest, which we call it static, the object is static, or the object is moving with a constant velocity, meaning the speed of the object is constant and the direction of the object is constant. This is translational equilibrium. The same thing with rotational equilibrium. Rotational equilibrium means the angular. Now, if the sum of the torques is 0, this means the angular omega is either 0, and this means the object is not rotating, no rotation, or it could be that the angular velocity is constant, meaning the object is rotating at constant rate. But if we say static equilibrium means the velocity is 0 and the angular velocity is 0. So both v is 0 and omega is 0. And the same way when we talk about work related to translational motion, we define work as force times displacement, recall. So now we replace the force by the torque for the work done by angular motion, which is work done by torque. We replace the force by torque, and we replace the displacement by the angular displacement, which is delta theta, where theta is the angle. And in all those cases, we have to use radians for the angle, so be careful about that. And the same way we define impulse in the case of linear motion, the external force is the rate of change of momentum, delta p over delta t, which means that if external force times delta t equal to the change of the linear momentum. In the case of rotational motion, we can replace the external force by the torque. That's the average, this symbol here. The torque times the change in time. Since P is mv and m is constant, we can rewrite the equation here. The external force times delta t equal m times delta v. So we can apply that on the rotational motion. So instead of external force, we have the torque. Delta t will remain as it is. Instead of the mass, we have I. Instead of delta v, we have the change in the angular velocity. This term here represents the change in the angular momentum, because this one here represents the change in the linear momentum. This one here represents the change in the angular momentum, and we call the angular momentum L. So this is the change in L, where L is the angular momentum. And hence we can define the angular momentum as I times omega. The same way, the linear momentum is mv. Instead of m in linear motion, we have I in the angular motion, in the rotational motion. And instead of v in the linear motion, we have omega in the rotational motion. And of course, P will be replaced by L, where L is the angular momentum. And the same way in the linear motion, when the external force is 0, the momentum is conserved, the linear momentum is conserved. Also in the rotational motion, if the net torque is 0, then the angular momentum is conserved, meaning the sum of the angular momentum before the event, any event that is equal to the sum of the angular momentum after the event. So this will be the initial angular momentum, and this will be the final angular momentum, because angular momentum is moment of inertia times the angular velocity omega. Finally, chapter 12, equations. This is the equation of gravity between any two objects. This is important here to understand that this is the main equation of gravity. It's not the equation that we learned about the weight. If you recall, we defined the force due to gravity for an object on the surface of the Earth as m times g. This is just a special case from this equation. Recall, this equation is applied for any two objects in the universe. Like if you have any two objects, m1 and m2, they are attracted to each other by a force of gravity, which is a force of action and reaction, equal in magnitude, opposite in direction. And this force of gravity, this attraction between M1 and M2, is equal to a constant g times the mass of the first object times the mass of the second object divided by the distance square between the centers of those two objects. So r here does not represent radius, it represents the distance between the centers of the two objects M1 and M2. Now, for a person standing on the surface of the Earth with mass m, the mass of Earth is m sub e here. If we apply the general equation of gravity, this equation here, it will be simply, so this is the force of gravity between a person standing on the surface of the Earth that has mass m and the mass of the Earth. In that case, applying this equation will be g times the mass of the Earth times the mass of that object or that person in that case, divided by the radius square. Now the radius square here is the radius of the Earth plus the radius of that person, but if we assume that that person is very small compared to the radius of the Earth, this will be the radius of the Earth, and this will give you the same as this equation. And we can prove it. If you take m here, this is m here, and g times the mass of the Earth divided by the radius of the Earth square, this will give you g. This is actually equal to 9.8 meters per second square. Okay. So actually, the equation of weight, which is force due to gravity, is a special case from the universal law of gravity. All right, let's assume we have the following question, which is one of the questions in the review. And make sure to go over the questions in the review as well as the clicker questions for the multiple choice questions. And now this is one of the problems in the review, and I want to show you how to go about solving any problem using what you learned and starting from the formula sheet. So for example, in this problem, you are given the mass of the Earth. So we start always by recording what we are given. And the mass of the Earth is 5.9723 times 10 to the power 24 kilogram. And the radius of the Earth at the equator. So you are given the radius of the Earth. And the question is, what is the speed of a satellite in an orbit around the Earth at an altitude of 3,800 kilometers above the surface of the Earth? So in part A, you are asked to find the velocity of the satellite. And you are given that the satellite is an altitude. So this is the distance from the surface of the Earth to the satellite, and it's 3,800 kilometers, 4 significant digits here. Notice here you can go ahead and convert right away the kilometer to meters, since we are given the radius here of the Earth in meters, and here the kilometer. So we know at one point we have to make sure that the units are consistent, so you can do it right away here. Now you know that kilometer is 1,000 meters, so you multiply 3,800 by 1,000, and this will give you 3.8 times 10 to the power 6 meters. So let's imagine the problem here. So we can imagine here the Earth, and we have the satellite some point above the surface of the Earth. We are given this distance d between the satellite and the Earth, and we are given the radius of the Earth. Now let's discuss the physics here. So you need to understand what's going on. You should know from your study that this satellite is in orbit around the Earth, and in order to be in orbit around the Earth, it has to be moving with certain velocity v, and it has to be under the influence of centripetal force downward. Now we know centripetal force has to be equal to a certain force. It's in the case of a car making a turn, it will be the friction. The friction will be the centripetal force. In the case of rotating a cup of water, the tension on the string will be the force. Now in the case of an object in an orbit around the Earth, the centripetal force is actually the force of gravity. And for this object to be in an orbit around the Earth, the force of gravity has to be equal mv squared over r. For the satellite to be in orbit around the Earth, the force of gravity applied on it, which is the centripetal force, has to be equal to mv squared over r, where v is the velocity of that satellite and m is the mass of that satellite. Now, if we go back here to the equations, now if you look at the formula sheet, suppose you forgot the centripetal force formula. This is the centripetal force formula here. So we know this is the formula that has the velocity related to the centripetal force. And if you forgot the force of gravity, you have it here in the formula sheet. If you go down to chapter 12, gravity, this is the general equation of gravity that we need. Okay, so those are the equations we are going to take from the formula sheet. The equation of gravity and the equation for the centripetal force. And we know in order for the object to be in orbit, the force of gravity has to be equal to mv squared over r on that satellite. So now we'll go ahead and set the force of gravity, which is g times m1, where m1 is the mass of the satellite, times m2, which is the mass of the Earth, over the distance square between the center of the Earth and the center of the satellite. So r here represent the distance from the center of the Earth, starting from here, this is the center of the Earth, to the center of the satellite. This distance here, from the center of the Earth to the center of the satellite, is what we need to plug into the equation. And this simply will be the radius of the Earth plus this distance. This should be equal to mv squared over r here. So this is the left-hand side. Now the right-hand side, mv squared over r. So this is the mass of the satellite times the velocity square, the tangential velocity square of the satellite, over r, where r here also represents the distance from the center of the Earth to the center of the satellite. This is how far the satellite is from the center of the Earth. So this is r here. Those two r's on both sides of the equation. So now we can do some simplification by canceling the common terms on both sides of the equation. So the mass of the satellite m here will cancel out. You should not worry that we are not given the mass of the satellite, because we are not going to need it since it will cancel out. And the square here will cancel out with r. So we'll be left with v squared equal to g times the mass of the Earth over r, where r is the sum of the radius of the Earth plus the distance between the surface of the Earth and the satellite. If we take the square root of both sides of the equation, v will be equal to the square root of g times the mass of the Earth over the distance from the center of the Earth to the satellite, which will be the radius of the Earth plus that distance between the Earth and the satellite. And now we can go ahead and plug the numbers. Here you should see that we were able to set up the equations by first finding what we are given and then solving for the unknown using the equations in the formula sheet. So now we go ahead and plug the values. Now g is given to you in the formula sheet. It's 6.67 times 10 to the negative 11 Newton meter square over kilogram square. The mass of the Earth, which is 5.9723 times 10 to the power 24 kilogram, over the radius of the Earth plus the distance from the Earth's surface to the satellite, which should be 6.378 times 10 to the power 6 meter plus 3.8 times 10 to the power 6. This is all in meter. Now, if you carry out the calculations, apply the square root, V will come out to be meter per second. Now, why the answer is meter per second? If we look at the units, we have Newton, and Newton is kilogram meter over second square, because Newton is force and force is mass times acceleration. So unit of mass is kilogram, unit of acceleration is meter per second square. So this is Newton here times meter square times kilogram over we have kilogram square in the denominator and we have meter in the denominator. So we can see the meter in the numerator will cancel out with the meter in the denominator. Kilogram times kilogram will cancel out with the kilogram square in the denominator. And you'll be left with the square root of meter square over second square. This is the only two left, meter square over second square. So the unit will eventually end up to be meter per second. So this is how we got meter per second. This will solve part A of the problem. Now, part B, we are asked to find the period. Now, how can we get the period? The speed is distance over time. And here, to complete one revolution around the Earth, the satellite has to travel a distance equal to the circumference of its orbit. And we know the circumference of any orbit is 2 pi times the radius of that orbit, the radius of the orbit. And of course, the period is the time taken to complete one cycle, which is one revolution. So the time here is the period, uppercase T. Hence, we can find the period by rearranging this equation, multiply both sides of the equation by T, then divide both sides of the equation by 2 pi times R. This will give you the period equal to 2 pi times the radius of that orbit over V. Now, we already established that the radius of the orbit is the sum of the radius of the Earth plus the distance between the satellite and the surface of the Earth. So T equal to 2 pi times the sum of 6.378 times 10 to the power 6 plus 3.800 times 10 to the power 6, and those all are in meters. This is all divided by V with 6.25 times 10 to the power 3, going with 3 significant figures. Now we'll go ahead and plug the value of the velocity. And now you can see meter will cancel out with meter, and then you have 1 over second, so the answer will be in second, and this will yield that the period equal around 10,200 seconds if we go with 3 significant figures. And then you can convert the answer here to hours, since we are asked to find the period of this satellite in hours. So it will come out to be around 2.83 or 84 hours. So this is just a sample exercise here of how to go about solving problems and how to show your work so that you can get credit even if you did some error in the calculations. Thank you, and please let me know if you have questions.